Hello everyone. In this video we're going to be solving a logarithmic exponential equation. Sort of. We have a to the power ln b times b to the power ln a equals 16, and we're going to evaluate ln a times ln b. We're not going to find the values of a and b separately because we only have one equation and we're not necessarily looking for integer solutions. So it's not a Diophantine equation. So we're going to try to find this expression from the given expression. Make sense? So I'll be presenting three methods, and this time let's start with the first method. So for my first method, I'm going to do the following. I have a to the power ln b times b to the power ln a equals 16, right? That's the expression. I'm going to go ahead and ln both sides. Why? Because I want to bring those powers down, and that makes sense, right? Hopefully. If you are lning a product like ln xy, that turns into ln x plus ln y, as long as x and y are both positive. So this expression turns into ln a to the power ln b plus ln b to the power ln a equals ln 16. Awesome. Now we can go ahead and move the powers down. That was actually the goal, why we ln both sides. When you do that, you're going to get the following. ln b times ln a equals, not equals actually, that is a plus sign, plus ln a times ln b equals ln 16. Interesting. Aren't these two expressions equal? They are, right? It's just the commutative properties. So this means 2 times ln a times ln b is equal to ln 16. So we're looking for ln a times ln b, which is half of this. So ln a times ln b is ln 16 divided by 2. Okay? Now we can simplify this because 16 can be written as 4 squared, and then we can move the power one more time. This becomes 2 ln 4 divided by 2. 2 cancels out, and we end up with ln 4 as the answer. All right, so let's go ahead and take a look at the second method. So first method basically used the idea of lning both sides. By the way, ln is the natural log, so when I write ln x, it just means log x with base e, and e is Euler's number, and it's about 2.7. That's all I know. Okay, an interesting number indeed. So that's what we did for our first method. ln both sides and just proceed with the solution. How about the second method? So for our second method, obviously I'm going to rewrite the original problem. A to the ln b times b to the ln a is equal to 16, and we're supposed to evaluate ln a times ln b. So for my second method, I'm going to do the following. I'm going to go ahead and add actually use substitution here. So but here's a very nice property of logs that we're going to use, and this should be well known because we use this in very many different videos, and you should hopefully know this before then. A to the power ln b is always equal to b to the power ln a. So when you switch the a's and b's, you get the same thing, and you can just prove that by lning both sides or doing some other properties of logs, but easy to prove. So let's go ahead and set each one of these equal to t, since they're equal to the same thing. So now if you replace like each one of these with t, this is t and this is t. By the way, tea is a really good drink. Anyways, black tea especially in the morning. So replace a to the power ln b with t, you get t squared equals 16. Now this gives us two results. T is 4 or t is -4. But guess what? T cannot be -4. A and b are both positive. Why? Because in order for the ln function to be defined, well defined, a and b have to be positive. Therefore, the base is positive. It can't be negative. -4 is impossible, so we're going to go with 4. But what is that supposed to mean? It just means t is 4, so we can take one of these. Doesn't matter which one. Let's go ahead and use a to the power ln b equals t, which is 4. Awesome. What am I looking for? I'm looking for, okay, I'm not looking for the 4 because I have 4, but I'm looking for ln a times ln b. So what do? ln both sides, right? It's always helpful, almost always. ln a to the ln b. So if you have a log problem and you don't know what to do, just ln both sides. But obviously it doesn't always work, right? We had a problem like this a while ago, right? A long time ago. I think this was the problem that has been watched like 2.5 million times or something like that. Anyways, advertisement break, commercial break. So yeah, for this one you can't log both sides because we can't log a difference. Anyways, so this is when you ln both sides here, you get ln a to the power ln b, this whole expression being ln equals ln 4. Now you move this power to the front and guess what? You'll get the answer. So that's kind of nice. I like this method because it gives you the answer directly. And this is what we were looking for. So the answer is ln 4. Let's go ahead and take a look at the third method. So the second method was we didn't ln both sides. We used substitution, but at some point we ln both sides. Why? Because it's helpful. You can also solve without lnning both sides. You can use the definition, pretty much the same thing. All right, let's go ahead and continue with the third method. And guess what? At the end, I'm going to show you a really cool graph. All right, so we have a to the power ln b times b to the power ln a equals 16, and I'm looking for ln a times ln b. That's the original problem, right? Okay, what am I going to do? I'm going to use substitution again, but this time I'm going to use it in a different way. What I'm trying to find, I'm going to call that something. So how about calling this x, ln a times ln b. So this gives us two things. ln a times ln b is equal to x, and ln b times ln a is equal to x. Why am I writing it twice with the factors switched, right? Because I'm going to use a really cool property of logs, and which is something that we've been using over and over, but this time it's going to be backwards. Let's go ahead and make this a power because we can, right? It's like, why do we do this? Because we can. All right, that's the only reason, right? So we can go ahead and put these here as powers, because when you have a power, you can move it. So in other words, like if you have something like ln x to the y, it becomes y times ln x, and y times ln x can also be turned into ln x to the power y. Same thing. Okay, now notice that when I move the ln a as a power, ln b to the power ln a becomes x, and from here I get ln a to the power ln b equals x. Again, don't get me wrong, they're not equal to ln x, they're still equal to x because we haven't ln both sides. We just set them equal to x, right? Now what am I going to do next? I'm going to be using properties of logs, or should I say definition? Yeah, okay, let's call it that. We have the base e, so if you go ahead and use the definition, e to the x equals b to the power ln a. From here, same thing, base is e to the x equals a to the power ln b. We knew that they were equal, but this also verifies it, right? Now, what do I have? I have that their product is equal to 16, so a to the power ln b is e to the x times e to the x is equal to 16. E to the power 2x is equal to 16. Square root both sides, e to the x is equal to 4. How does that help? What was I trying to find? I was trying to solve for x because guess what? This is what I'm looking for. So you can use ln both sides again, right? ln, and we get x times ln e, which is 1, x equals ln 4. So that's verified one more time. Let's go ahead and take a look at the graph. I wanted to share with you real cool. I believe I shared this with you, I think a while ago. This is maybe one of the posts, but anyways, this is kind of cool. It's the graph of x to the power ln y equals y to the power ln x, which is pretty much the whole first quadrant, but it's not fully resolved because there are so many data points and Desmos can only do so much. But guess what? As long as x and y are positive, this is pretty much everything. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you tomorrow with another video. Until then, be safe, take care. Don't forget to watch the shorts, and bye-bye.